everyone, and welcome to the Webb Community Events Expert Panel for August 14th, 2022. Today, we're going to talk about Webb's first images. And with me, I have a panel of experts. My name is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute. With me today is Lou Strolger, who is a scientist at STSCI working on supernovae and other transients. And he's interested in what these events tell us about the history of the chemical enrichment of the universe. We also have Alyssa Pagan, who is a science visual developer who works with me in the Office of Public Outreach at the Space Telescope Science Institute. She uses her background in art and science and creates colorful images of space that both inform and showcase the beauty of our universe. Christine Chen, who is the James Webb Space Telescope Science Policy Group Lead and an Associate Astronomer with tenure at the Space Telescope Science Institute. She uses multi-wavelength observations, including those with Webb, to understand how planetary systems form and evolve. We have Kevin Stevenson, who is an exoplanet astronomer at Johns Hopkins Applied Physics Lab, where he enjoys working with the boundary between planetary sciences, astrophysics, and astrobiology. He's been studying the atmospheres of gas giant exoplanets and is now looking forward to using Webb to study the atmospheres of small rocky planets. And finally, we have Casey Papovich, who is a professor of physics and astronomy at Texas A&M University. He has worked on studying the formation of galaxies and using NASA's space telescopes for more than 20 years. So with that, I'm going to ask Lou to start us off. Could you introduce yourself and tell us a little bit about how you got where you are today?
Oh, sure. Thanks, Kelly. So I'm Lou Strolger. I am an observatory scientist at Space Telescope, as Kelly already mentioned. And I'm also the deputy head of the instruments division at the Institute. How did I get here? That's a pretty interesting question. I started off thinking more about computers in my early career and fell in love with astronomy through frequent visits to museums when I was a kid. As each opportunity came to study more astronomy, I kept doing it and doing it and doing it. And one day I woke up and I was a grad student, PhD candidate at the University of Michigan, looking through large telescopes, trying to understand how supernovae tell us about the expansion rate of the history, or expansion rate history of the universe. That sort of led to a career where I, from one thing after the next, one postdoc to the first faculty position to this position, I just sort of stayed the course, studying more about astronomy and trying to understand more about the things I love.
Okay, great. Thank you. Christine, same question. Could you introduce yourself and tell us about how you got where you are today?
Thanks for that, sorry. I grew up in a scientific household. My dad was a scientist, and so from a young age, I saw that my dad was really satisfied, really enjoyed what he did for a living, and I found that really inspiring. I remember he would tell me stories about how things worked when I was growing up, and I really enjoyed that. And so when I went to school, I thought, hey, I want to be a physicist just like my dad. And then I got to school and I was like, maybe not physics. And, I would hang out with the astronomers, take classes with astronomers. And I thought, wow, that's super cool. They get to go out and actually look at the sky and see real things that are out there that we can't see with our eyes. That's so awesome. And so I chose to go to graduate school in astronomy and had a fairly traditional path, graduate school, postdoc, before going to a permanent position at Space Telescope, which is a great place to work. Yeah.
Agreed. Okay. Kevin, could you go next?
Yeah, not a problem. Similar to Christine, I was doing my undergrad in physics, And I realized that maybe that wasn't the path I wanted. I ended up taking an undergraduate course in astronomy, and I was just blown away at all the excitement and potential opportunities coming around. It was a year later when I actually went to a colloquium by a professor who had talked about these amazing things called exoplanets, which I wasn't familiar with at the time. And I thought, you know what, this is what I want to do growing up. So I followed him to the University of Central Florida. It was 2007, so back then we could count on our fingers and toes just how many exoplanets there were back in the day. And we've sort of come a long way since then. I remember when we hit milestones of 1,000 exoplanets back in like 2014. When I got a job at Space Telescope Science Institute, I was preparing to work on the James Webb Space Telescope Science as part of the team there. And I remember we hit 3,000 exoplanets, and I thought that was just phenomenal. But nowadays, things are chugging along. We've got 5,000 exoplanets and counting. I think Kepler and Tess have done an amazing job at discovering some of these exoplanets over the years, and really looking forward to seeing what JWC can do in the future. This is, the critical time where we can actually study the atmospheres of these planets. So really looking forward to that path forward.
Trouble with Casey. So why don't we move on to our next speaker? Alyssa, could you tell us a little bit about yourself and how you got to where you are today? It's a little different, I think, than the rest of our panelists.
Yes. So for some reason, if I turn my camera off, I can't turn it back on. I don't know, but that's okay. You don't need to see my face. Just to throw a little wrench at everything, I kind of have a meandering path. As Kelly said, I'm a science visuals developer for Space Telescope Science Institute, and that just means that I take astronomical data from Hubble and now Webb and create full color imagery of that. And we do that to support press releases. We do that for educational resources and other outreach products. And so I actually started going to Towson University and getting a bachelor's in art and design. I really enjoyed art. I also really, really liked astronomy, but I didn't really pay attention to my math classes in high school. And I didn't really think I was going to go in that direction, but I was obsessed with astronomy documentaries, and I would watch that over everything else. And so actually when I finished my degree at Towson University, since it is a liberal arts college, you do get some core experience in, the math. And I'm like, oh, I'm not bad. I just haven't been paying attention. So it was kind of like a life-changing thing for me to know that you can learn whatever you want to learn as long as you, put some effort into it. And so I decided I was going to pursue another degree in astronomy at the University of Maryland in College Park. Honestly, had no idea how these two different things at the time would come together until I took observational astronomy. And that's where you took your own data, made your own observations, performed your own data analysis, data reduction, and then produced the full color images. And it dawned on me that someone's doing this for Hubble right now. And like, how do I get my hands on that? And it was like the first time I really saw like there is a way to incorporate and leverage both science and art. And so I pretty much set my eyes on the Space Telescope Science Institute since it was local to me, and I heard about their outreach team. And basically stalked them for like 2.5 years until the science visuals developer position came open. And it's pretty much like the job description was like art, science. And I'm like, yes, please. So yeah, and here we are. It's been awesome.
Great. And I'm sure we'll have lots of questions for you. Okay. Maybe, Casey, we can try it again. You broke up a little bit halfway through.
Happy to, and we'll just bless the internet and all of the phenomenal things it provides for us. So I don't know how much of you heard from me before, but I'll try to keep it brief. So I'm Casey Papovich, and my path to this, I think, mirrors a lot of that of my colleagues. So as a young child, I was very interested in astronomy, just from learning about it from the first parts. It showed that the universe is very different in the past, and that we can actually study that and learn from it by looking at images from telescopes. And so I first went to school for physics. I think like many of us here, no one encouraged me to get a job in astronomy because they said, oh, what are you going to do with that? But then I went to graduate school there at Johns Hopkins, right around the time the Hubble Space Telescope was providing the first images from the Hubble Deep Field. And I think that just wowed me into it, that we could actually see the evolution of the universe and that the properties of galaxies in these extremely distant images were vastly different than what we see today. In fact, galaxies were much more active in the past than they are now. And so I think that just pulled me in that direction. And so I started first working with the Hubble Space Telescope data for my thesis. Then I moved to the Spitzer Space Telescope in the early 2000s. And now I teach astronomy and physics, and I get to use the James Webb first images to carry on this science. I'm really excited to be here to talk about it.
Okay, great. So talking about science, why don't we move on to our first image, which is Webb's first deep field. So if you could go to slide 2. Great. And Casey, why don't we continue on? Could you describe this image for everyone and what you see as a scientist looking at it?
I'll do my best. So I was in the room on Johns Hopkins campus when they put this image up, and it just wowed us all at an astonishing level. So what you're seeing here is an extremely small patch of sky imaged by the James Webb Space Telescope in multiple, what we call filters, which just give us the color information that you see here. So what our eyes perceive as the color is actually telling us how much light the galaxies are emitting in this image at different wavelengths. And so what are we seeing here? Well, there's several things. So the prominent six-spiked object right in the middle, that's a star in our own galaxy. And that draws your eye to it, but that's actually what people like me ignore, and we work very hard not to look at those kinds of things. What we're really interested in are the objects in the background. And so this image, all of those things are galaxies. Nearly everything in there is a galaxy, except those things with those little six-sided spikes on them, for example. And so you're seeing an entire snapshot taken over the history of the universe. And what do I mean by that? Well, what I mean is most of the objects in this image are billions of light years away. The most distant ones are 14 billion light years away, or almost right at the age when the Big Bang occurred. We're seeing the first objects to form in this image, but we see them all in the same image. Now, how do we get to use that? Well, light is fast, but it travels at a finite speed. And so when we see a galaxy that is 10 billion light years away, the light has been traveling to us for those 10 billion years. And so we see that galaxy as it looked when the light left it. And so the James Webb Telescope is collecting that light and gives us an image of what that galaxy and what the universe looked like 10 billion years ago. And so in an image like this, we can actually see galaxies over an enormous range of cosmic time. There's some galaxies that are relatively nearby. Those things are only a few billion light years away. But then the faintest objects in here, the ones that James Webb can now detect, are almost as old as the universe itself. And Kelly, I'm happy to go into more details about that. There's a lot of more information in here. I don't know what level you'd like me to continue. I'll ask you for guidance before I go on.
Okay. No, I think that was a really great introduction to this image. I'm waiting now to see if any questions are coming in. So as a reminder, all of the host sites, you should have had a link in order to submit questions to our panelists. So you can go ahead and do that. And if you'd like, you can also mention where you are so we can read that out when we're reading your questions. So I guess I want to give everyone a chance to speak if you want. Are there any other members of our panelists who want to talk about seeing this image for the first time, or what sort of science you're excited to come out of Webb's first deep field?
I can chime in there.
Okay,
this is more
great.
of from an image processing standpoint, or even just like an outsider looking and being able to describe like the image to the general public. I was at this event for NASA, which is the National Air and Space Museum, and it was so cool to talk to people walking by, and the participants were like, looking at this and blown away by how many galaxies there were. And I was kind of asking them, like, how far across the sky do you think this region of space spans, essentially? And a lot of people were like making, very wide gestures, which makes sense, right? Because there's so many galaxies, you'd think it would take up a huge part of the sky. But then I pretty much blew their mind when I was like, this region of sky is just a grain of sand held at arm's length. And like everyone was just like, what? and like, you know, there's like an existential moment that everyone has, and it's just super cool. So that's just one thing that I like to throw in there, because it just really, you see the awe and just the scale of space. Super cool.
If I could chime in, there's another thing that I think is really impressive about this observation, and you can't tell it from looking at the picture. All of the data that went into this image, there are images taken in multiple wavelengths, multiple filters that are combined to create this color image. All of that data, it took 12 and a half hours to accumulate that data, which is absolutely remarkable, because you're seeing farther back in time, at least as far as Hubble did in the same image. And the images of the deep fields from Hubble took weeks of time to take. And so basically this is really demonstrating that JWST, what JWST can do in hours took Hubble, or it took Hubble days, essentially. So that's one of the reasons why JWST is so powerful, and we'll be able to really look at the first stars and the first galaxies.
Cool. Okay, we have our first question. This comes from the Palouse Discovery Science Center in Pulliam, Washington. Just how many galaxies are we looking at in this deep sky image?
That's an excellent question, and I'm happy to give that one a go. There are, so you could try to count them, but there are thousands of galaxies in this individual image. Some of them are relatively nearby, and those are the larger ones. They actually look physically larger, and they're just closer to us, so they look bigger. And then some of them are even more distant. If I can go on about that, so there are thousands of galaxies in this image. What you see, because they span a range of distance from us, we get other perspectives. So this has this object, this field, is called SMACS 0723. That's a catalog number, but it's really centered on what's called a galaxy cluster that is relatively nearby, maybe only about 6 billion light years away. That's relatively speaking. And so those are kind of the whitish galaxies you see right in the middle. This galaxy cluster consists of maybe hundreds of those objects, and they're all gravitationally bound together. And this is one reason they wanted to use this as a test case for James Webb, because all of that mass that is associated with those galaxies actually bends space around it. This is a prediction from general relativity from Albert Einstein, more than 100 years ago. And in fact, we have a slide, I think, that demonstrates that. Can we go to slide 9, Travis? Yeah, here we go. So on the left, you actually have a little cartoon illustration where those white fuzzy things in the middle that are labeled galaxy cluster, those are the hundreds of galaxies that are gravitationally bound together. It illustrates that. And then what happens is that the galaxies that are more distant, they're behind it. Because their light gets bent by the gravitational mass of the galaxies in the cluster, we actually see them magnified. We see both their light gets magnified and their images get distorted, just like you would if you looked through a glass or a curved shape of often like a wine glass is a good example. If you look through a curved glass, you'll actually see the world gets distorted. And the mass associated with this galaxy cluster is doing that. And so on the right, you actually see then images from this James Webb image of these distorted background galaxies. And you'll notice they get stretched and elongated. That's part of this gravitational magnification and lensing. And as well as their light gets increased as well. So we get all that information. So it's nice because, one, it's actually proving that general relativity works, and it gives us a better ability to see what's going on inside those background objects, which are illustrated there by that arrow.
Yeah, really cool, really exciting. Okay, so I think in the interest of time, we're going to move on to our next observation. So we're going to slide 3. And we're going to talk about the exoplanet WASP 96b. And I guess I'm going to ask Kevin to talk about this series of images.
Thanks, Kelly. Yeah, before we get to the transmission spectrum of WASP 96b, I think it's only polite if I give you a bit of a primer on the planet itself so that we get to know it a little bit better. WASP 96b was discovered back in 2014, so it was in the realm of, one of 1,000 known exoplanets back in the day, and it was pretty typical in the sense that it's a hot Jupiter. Maybe not typical in terms of the number of planets we have known now, but back in the day, most of the planets we had discovered were relatively large and orbited around their host stars on very, very short orbital periods, on the matter of days. So this planet is about 1,800 degrees Fahrenheit, which is far hotter than your hottest oven or barbecue, and it orbits around the star in 3.4 days. So it moves around very, very quickly. You can imagine celebrating your birthday every 3.4 days. That would be quite a lot of fun, in my opinion. So we looked at this system back on June 21st, about 8 weeks ago, and what we tried to do is observe the planet as it crosses in front of its host star. So this is what's depicted up top there, where we have the planet orbiting around the star, and just through chance alignment, it happens to cross in front of the path between the star and the Earth. And so what happens is, in the plot below, it shows the brightness of the star when we first begin our observations shortly after midnight. And then as the planet starts to cross in front of it, there's that dip that you see around 2:30 in the morning. And then as the planet fully crosses in front of the star, it then leaves around 5 o'clock in the morning, and then we see the starlight after that. So this is what we call a transit, this decrease in light as a function of time. And what happens is we can measure the depth of this transit, essentially the bottom, comparing the top minus the bottom, and look at that at different wavelengths. And so the question that we have to ask ourselves is, what causes this change in depth or change in apparent size of the planet as a function of wavelength? Well, that's actually the molecules, the chemical compounds in the atmosphere itself that are causing this change. So if you have molecules like water or methane or carbon dioxide, each of them absorbs at different wavelengths, making the planet appear smaller or larger based off of how much water or methane or carbon dioxide is in that atmosphere. And so this really leads us to being able to understand the atmospheric composition of these planets just by looking at this dip in wavelength and comparing it to different wavelengths. So if we can go to the next slide, I'll show you the transmission spectrum of WASP 96b. Here it is in all its glory. This, I will tell you, took my breath away when I first saw it. It was absolutely amazing. I could not believe how stunning, how precise the spectrum was. These white data points that you're looking at here, each of these is an individual measurement of that transit depth, the size of the rate of the planet as a function of wavelength. And you can see here that there's all these sort of bumps and wiggles going on throughout the wavelength space. And what's causing that? Well, it's water vapor in the planet's atmosphere. And you can see that with this blue model that we've overplotted on top of the data here. And all of these bumps and wiggles really match up very well with the expectations of water vapor within the planet's atmosphere. Now, of course, it doesn't match perfectly at all these places, but you know what? That's okay, because that just means that there's more physics going on in the planet's atmosphere than what we have currently modeled. It's a very sort of simple model that we've started with here. And as you add more and more molecules and more interesting chemistry and perhaps clouds and aerosols and hazes, you can build up to more complex models. And it really allows us to understand these planets more. So this is just the first step in terms of modeling these planets' atmospheres. And we really look forward to the next steps. We'll be adding more physics and learning more about these planets as we move forward. So I think I'll stop there before I say anything else and see if there's questions.
Yeah, so I am still waiting for questions from the audience. Any of our other panelists want to chime in? Oh, here we go. We have a question. So why don't we ask that one first? So this again comes from the Palouse Discovery Science Center. how many exoplanets has Webb been observing thus far, and how much time does it intend to spend hunting and observing them?
Yeah, so far we've looked at probably about 10 exoplanets in the last 8 weeks, and they range in size and temperature from these hot Jupiter-like planets, like the WASP 96b that you see here, all the way down to much smaller, much cooler planets like those in the TRAPPIST-1 system. So for those of you not familiar with TRAPPIST-1, it is a small red dwarf star that's very cool, that has 7 known transiting planets, all of them in around the size of the Earth. So they're rocky in size and could potentially have, oxygen, nitrogen, or carbon dioxide type atmospheres. And JWST has started observing transits from planets in that system. Now, it may take some time for us to learn about the compositions of these atmospheres, or whether or not they even have atmospheres, because we need to take a lot of transit to sort of build up the signal to get more photons. So it may be 6 months or a year before we are starting to learn about these rocky planets, but we will get there and we will learn a lot about them. In terms of how much time we're spending, roughly 20% of JWST's time has been allocated towards studying the atmospheres of exoplanets. So we can look forward to essentially hundreds and hundreds of hours of telescope time in this first year alone dedicated towards exoplanets.
Okay, so I'm going to ask a question that I got at a public talk that I gave the other night. I thought it was a good one. So why are we seeing water first? Why didn't we detect some other molecule for Webb's first exoplanet observation?
Well, that is a great question. So the instrument that we're using here is nearest SOS, and it has a very specific wavelength coverage here. You can see it's about 0.7 microns, which is sort of on the edge of what we can see with our eyes, all the way out to about 2.8 microns, which is very solidly in the infrared. It just so happens that at these wavelengths, the most dominant molecule, the easiest molecule to find, is water. Its molecular features stand out very, very clearly compared to all of the other molecules here. So that just happens to be the molecule we detect first. Now, if we had looked at longer wavelengths, Spitzer wavelengths, for example, maybe from 3 to 5 microns, then maybe the first molecule could have been carbon dioxide or methane or even carbon monoxide. So it's just a byproduct of the instrument that we're using, and I fully expect that when we see spectra at other wavelengths, we will definitely be detecting other molecules.
Okay, great. There's some great questions, but I want to make sure that we have time to talk about all of the images. So we are going to move on. So we're going to talk about the Southern Ring Nebula next. And Alyssa, if you could tell us about this image and what you see when you look at it.
Yes. So yes, as Kelly said, this is the Southern Ring Nebula, and it's called a planetary nebula, even though it has nothing to do with planets. This name actually was named Planetary because astronomers back in the day would use, not as good telescopes as we have now, look at the sky and they'd see like a fuzzy blob where they saw like a planetary nebula that looked kind of like a planet. So like, okay, we'll just call it a planetary nebula because it was kind of circular. But this is actually a star at the end of its life, and it's ejecting its surface because it's lost its battle against gravity, essentially. And what's really cool about looking at stuff like this is you're actually kind of seeing our future, the future of our sun. And so when you look at stars at the end of its life, depending on sort of its mass, you are actually learning the whole timeline of stars and their evolution from very beginning to the very end. So Webb is looking at, the youngest stars. It's looking at the dead stars, essentially. So we have two views of this nebula. We have it in NIRCam, which is a near infrared light, and then we have it in NIRI, which is really cool. In the left with the NIRCam, you see like just the structure that you could see, like it's just so detailed, and it's really fun to process these images too, because you're using what we call narrowband filters, and that just means that we're collecting very specific wavelengths of light, and we're showing sort of the composition in these particular areas. So those colors actually represent sort of atomic transitions or like elements, gases, specific gases that you're seeing there. And it's really cool. And on top of that, just an added bonus with any Webb image is you're getting some background galaxies because, you know, that's what Webb does. So it's very, very cool to see this, and then also compare it to the image on the right with the mid-infrared, and you kind of see that, oh, wait, it's not just one single star in there, it's a binary system. So you have your white dwarf, and then you have like this little red dusty guy that shows up there. So it's really cool that you can see how it's important to see in different wavelengths of light just within Webb itself. And that doesn't go, that counts also for Hubble, which sees invisible. Like, just it shows the importance of seeing in all these different, across the electromagnetic spectrum, essentially. But yes, just a very, very fun image to process as well, and I think it's a very beautiful image. But that's all I have.
Okay, thank you. Is there anyone else, any of our other panelists want to chime in and talk about this image?
Yeah, if I can, there were two things that floored me about this image. Right, this is a perfect example of what happens when stars die. Right, you actually begin to see the history of their death, and if you look at the NIRCam image, it's most starkly it's very striking, as you can see all these little rings as you move out from the center that appear to be sort of artifacts in the image, but they're not. They're actually the history of stellar burping that was happening over time as the star began to slightly shed mass and then stop shedding mass and then slightly shed mass and then stop. Did this over and over again over millennia, and it's finally gotten to the point where it's built up this very rich image of just stellar shedding over time, almost like a cat, you know, just sort of leaving around hair every time it rolls around. It's kind of, in my mind, a very picturesque way of seeing that. The other, of course, is that in the MIRI imaging, you can actually see this very, very cool star at the very center, right next to the bright star that is very prominent in the NIRCam imaging. But the MIRI image actually shows this prominent deep red star, which is the actual white dwarf, which is shedding all this material in the first place. It's kind of very cool to see.
Very cool. Yeah, and so that star in the mid-infrared is really what's responsible for all of this gas, right? And you can only really see it in the near-infrared image. You can actually see it in the near-infrared image if you squint really hard, which is something that I only learned lately, which I thought was pretty cool. Okay, any other thoughts about the Southern Ring? I haven't gotten any questions about it. So why don't we, oh, here we go. I do have a question. Okay, in the Southern Ring Nebula photos, there are 3 distinct stars / images in the bottom right, a bright star lower right. Thoughts? So I guess this question is about, in the lower right, there is a bright star. Does anyone have any thoughts about it?
I guess my only thought was usually when you see bright stars in an image, it's a foreground, like Milky Way galaxy star. So it can be a little distracting, and a lot of people could be wondering, like, you know, where is that star coming from? But yeah, that tends to be like a photo bombing of a Milky Way star.
Yep, no matter where you look out, there's always a Milky Way star trying to photobomb your very pretty astronomical image. Cool. Okay, why don't we move on then to our next image, which is Stefan's quintet. I'm going to ask Lou if you could tell us what you know about this image and what it says to you looking at it as a scientist.
Sure, Kelly, thank you. So Stefan's quintet is one of my favorite targets out there because it's a great reminder that galaxies themselves evolve and interact over time. What you see is a group of what looks to be 5 galaxies that seem to be associated on the same pointing in the sky. It turns out that only 4 of them are gravitationally bound to one another. The 5th one, the one on the far, turns out to be a foreground dwarf galaxy, which is 7 times closer to the other 4 galaxies along falling along the vertical, but also is much, much smaller. And just because it's in the foreground and superimposed on these other 4, it appears to be roughly the same size and seems to be associated with the other 4, even though it's not. What I say about, it's showing how galaxies interact and how they evolve. You can see how these 3 in the very center, the upper left, or the upper galaxy and the ones in the center, are clearly interacting with one another. It's only hinted at, I would say, in the optical image, where you can begin to see some mending of the melding of the tails of the stripped, spiral structure, as it looks like or hints at some recent interaction. But that becomes very, very clear when you look in mid-infrared, where you see the dust, where it highlights the dust in between them, and clearly that history of interaction that wasn't that long ago. You also see these galaxies in different phases of their evolution. Due to the recent interaction, the galaxy on the upper side of the top of the diagram is actually has a very active supermassive black hole in the center. It's active, galactic, and because it's the nucleus of the galaxy, we call it an active galactic nucleus, or an AGN. And that supermassive black hole is getting new material, and at its current rate its current size is about, 24 million times the size of our own sun. So it's pretty massive and pretty big. As you move down through the image, the 2 spiral galaxies are clearly interacting with one another, shedding material. And the one at the very, very bottom is just an elliptical galaxy, which, even though is bound to the other 3, isn't really showing any signs of recent interaction. And then lastly, the one in the foreground it's actually just a dwarf galaxy, but it's so nearby that you can actually begin to resolve the independent individual stars that compose that galaxy. It's very, very striking when you actually see those individual stars and you zoom up and into the image and see them. With the previous Hubble imaging, you can almost begin to see them, but really only the globular clusters really stand out. Here, the stars definitely stand out. And then, I don't know who made this comment earlier, maybe it was Casey, but as every image with Webb is becoming a deep field unto itself, you can see the stark contrast of all these galaxies in the background. It's when I look at this image, I almost get a little fearful. I study supernovae in trying to find them. I know that supernovae happen roughly every 1 in 10,000 galaxies, which means that you can sift through a lot of images and not actually see one. But with Webb, the promise of being able to see supernovae in real time in almost every image is very, very real, and makes me realize I'm going to have a lot of work to do in the near future. But that's Stefan's quintet.
Cool. Anyone else have something to add? So if not, we got to, go ahead.
Kelly, I could chime in. I thought, so one of the things I remember, first of all, this is iconically beautiful. I think my colleague Lou described it really well. I was struck, I think you said this, Lou, about how much evidence there is for the interaction now between these galaxies that Webb provides. So the white imaging you're seeing here are the individual stars. That's light, it's not individual starlight, but it's a combined light from all the stars associated with the different galaxies. And the red is, as Lou pointed out, really tracing where the gas is. And those are just from images taken at different wavelengths. And so you can see through the interaction of these different objects where the starlight is following indicating the interaction. You see what we call tidal features, which are produced by a tidal force, the same force that causes the tides here on Earth, which is caused by the interaction between two gravitating bodies. And so you can see these little arcs associated with those interactions, as well as just the red light that's telling us where the gas associated with the past interactions as well. And in some cases, the gas sits outside of these galaxies, which is just all part of the fact that there's a lot happening in there.
Okay, great. So I got some good questions, and I want to see if I can squeeze them in here. So do we know the organic chemistry gases from the galaxies? And if so, whether the black hole will dominate these clusters? Maybe that's two questions, but so do we know about the chemistry of these galaxies?
I would say we are learning about the chemistry of these galaxies. We have these data came accompanied with some very interesting spectroscopy as well from the integral field unit. I'm not actually sure which instrument it was on, but there are a lot of spectroscopy that accompanies these data, and we are learning about the molecular structure, as that data builds up and people begin to study it. The question about the black hole itself is gaining mass, but it's still very, very confined to its own galaxy. It's actually very confined to a very small region that you can't even really resolve in these images. So there's no fear that it would gobble up these galaxies at any time soon. But it is actively feeding small amounts of gas, relatively small amounts of gas over time.
Cool. Okay, and so I have one more question I want to get to before we have to move on. So this came in earlier, but I think it's still relevant. So from the Canaveral National Seashore, with the telescope, the James Webb Space Telescope, can they do a closer examination of the galaxies closest to us? I think the answer is yes. We are seeing this. These are closer than the ones seen in Webb's first deep field. But does someone want to talk about what we can learn about by looking at nearby galaxies, like, for example, Stephan's Quintet or other nearby galaxies?
I can take a quick stab at it. I think the answer is a resounding yes. Webb is showing us a lot more detail simply because it has higher angular resolution than the Hubble Space Telescope could achieve. Webb is just larger, and so being larger, it can resolve individual structures better. And so as Lou pointed out before, like in these nearby galaxies, you're actually able to see individual stars or star clusters that would have just been blurred out, even in the best Hubble images that we had. And so that it tells us a lot more about the processes of star formation, the nature of individual stars, and we can test those against our ideas about how stars interact and form within galaxies at a much more detailed level than we've ever had before.
Cool. Okay, so we have to move on to our first image. So the star-forming region in the Carina Nebula, also known as the Cosmic Cliffs. And I'm going to ask Christine to talk about this one. What do you see in this image as a scientist looking at it? It's very beautiful, number one. But what about the science excites you?
So absolutely, this is a really striking image, and it's almost for me a little bit overwhelming how much is going on in here. We've heard a little bit about galaxies and how they contain both gas and dust. And this is maybe a little bit foreign to us when we think about our solar system and we have like planets and asteroids, we have large rocky bodies or gas giants, but there isn't really very much gas left over in our solar system. But if you travel outside the heliosphere, the bubble that the sun blows inside our galaxy, into the region in our galaxy between stars, there's actually quite a lot of both gas and dust. And there's about 100 times more gas by mass than there is dust. And this gas is mostly molecular hydrogen, and it is the material from which new stars are born. And essentially what you're looking at is a star-forming region, so a stellar nursery. This particular one is very close to our sun. It's in the southern sky, which is one of the reasons why we may be less familiar with it compared to Orion, which is in the northern sky. But you see at the bottom of the screen this yellowish, tannish region. This is part of a molecular cloud. So a region that's rich in gas and dust, from which stars are forming and maybe still enshrouded in their nurseries. And in this particular case, the color coding tells you how much dust is obscuring the stars. So the ones that are blue are in environments that are relatively free of dust, so they appear blue just the way that bare stars look to us. But if, for example, there's dust in front of them, that makes them have this sort of reddish color. So there's so much going on that I think it's really useful to zoom into like specific objects. So if we go to slide 25, I think it has some zoom ins of a couple of specific objects just to draw your attention to a couple of things. So these are sort of blow-ups of particular regions where you can see that not only are things, do they not just have different colors, but they have different morphologies, different shapes as well. And so, for example, on the left-hand side, you can see what looks like maybe a vase or something like that, a bowl in yellow. And that is actually material that is outflowing from a young star. So to try to understand what this is, it's useful, I think, to look at a cartoon. So if we go to slide 29, so this is just a diagram showing you the process by which stars form through this interstellar medium. So we start off on the top left and we move through the arrow. So we begin with a molecular cloud. So this is a region that is dense with gas and dust. And you can imagine that there might be some regions where the density is higher, there's more stuff. And so the gravity in that region can overcome pressure, and it can actually collapse under its own self-gravity. And so that's what you see as you go from A to B, is this collapse. You can imagine that as this collapse is occurring, that little knot of material might have a little bit of angular momentum or spin associated with it. And so just like an ice skater who is spinning, they draw their arms in, they start spinning faster and faster. The same thing happens with this collapse here, turning into, for example, a protostar, which you see in C. So now what's happening is it's spinning faster and faster, and the spinning, or the angular momentum, supports a disk of material around the star. That protostar at the center is still accreting material from the disk onto the star, so the star is building and getting bigger and bigger, the protostar is getting bigger and bigger, but some of the material that's getting funneled into the star is getting slungshot from, going through the disk onto the star, up or down, into what's labeled as the jet, or the broader part is called the outflow. So the jet is the really narrow part that's going up and down, and then the conical shape is sort of the outflow. And then over time, you can imagine all of this is happening embedded in the molecular cloud, but over time, the envelope dissipates. It becomes easier to see the disk and the star and the jet. And then eventually the planets, the star will stop accreting because the gas and dust will have accreted onto planets and the star. And then you'll see as you get to the planet formation phase E, how essentially the star is now stably burning hydrogen to helium in its core. And then the planets are, finalizing sort of the planetary system. It might have a lot of asteroids and comets in it early, which the planets kick out of the system. And then eventually you get to a solar system, which is F. But if we go back to, or actually embedded in this figure on the right-hand side, you can now see that excerpt from the original whole picture of Carina. You can see now that yellow sort of bowl shape corresponds to that outflow. And so what you can't see that's enshrouded in all of the dust in this molecular cloud, is where the protostar is and the disk around it. And basically, the jet is clearing material, and it's lit up by the central protostar. So you can imagine that, like, this is a really exciting region. It's not just one object forming in isolation. So if you go to the next slide, which is slide 30, this sort of gives you a better macroscopic idea of what's going on. So what I sketched out for you for star formation, or how a star forms, can happen for stars of a variety of masses, from very heavy stars that are several, to, tens as heavy as our sun, or things down to a fraction of our sun's mass. Typically, though, if you have these molecular clouds with lots of knots, you can imagine you could form a cluster of very massive stars all at once. And that's sort of what's depicted in the middle with all those blue arrows. And those stars that are so massive, they create a lot of UV radiation, and they may have strong stellar winds associated with them. And so they can actually blow a bubble in the molecular cloud in which they have been born. You can see on the left-hand side of this cartoon, there's open cluster and older open cluster. So these are older clusters of stars that have formed before the new cluster. And the new cluster, again, its UV, ultraviolet radiation, is impinging onto the molecular cloud. Its stellar wind is impinging on the molecular cloud. And it's as it's doing so, it's creating a ridge of sort of pressure and squeezing the molecular cloud there and creating new stars. So that'll lead to a generation of new stars being formed. So this is important in the context of Carina, because if you go back and look at figure 25 again, what you're seeing here is the bottom part is that molecular cloud, and the top part is that bubble that has been blown in the molecular cloud by a cluster of massive stars that are just off the field of view. And it's actually so spectacular, all the detail that you can see here, because the UV radiation from those massive stars is shining down onto the molecular cloud, and it's ionizing gas there, and that gas is very energetic, and so it's sort of evaporating upward, and so you can see these sort of streaks, which are really that ionized gas evaporating, in addition to just all of these amazing protostars and outflows that you can see in the image as well. So It's just a beautiful picture. Yeah.
That was great. I want to have time for one question before we
Sure.
move on. Okay, so this is a question, I think, for Alyssa. So are the colors in this image accurately depicted in RGB with JWST and specifics of NIRCam? So Alyssa, I guess if you could talk a little bit about color in these images and how you assign colors.
Yes, no, that's always a great question. Accurately is kind of a hard word just because we are dealing with infrared light, which is invisible to our eyes. So we're doing the best that we can, and you can think of it as sort of transcribing music. So if you, like, let's say you're playing in an octave of music that's like way beyond your hearing, and it's only dogs can hear it. And then you can transcribe it down to an octave that you can hear. And that's essentially what we're doing. So for like Hubble imagery, it's a little bit more straightforward, a little bit direct. We use something called chromatic ordering, and that just means that the shortest wavelength gets prescribed the bluer color, and then the longest wavelength gets prescribed the redder color, and in between it's green. And that's just the best representation of the visible spectrum. And we do the same thing with Webb. We make the shorter wavelength the bluest, and then the longest the red. And so we're essentially preserving sort of the relationships between the wavelengths, and we're giving you that full color image. Now, the accuracy, that's difficult. It's close as we can get. It's very representative, but it could be something that your eyes could see if you were as sensitive as Webb, of course, and if you were able to kind of parse those different wavelengths as color. So we're doing sort of the best guess that we can. It is always a balance between art and science, but we work very closely with the scientists to make it as accurate as possible, while also being like informative and compelling.
Okay, and I don't want to miss out on the newest, shiniest Webb image. So if we could go to slide 8, and we can look really quickly in our last 4 minutes at the Cartwheel Galaxy. So I think I said I was going to ask Casey if you could just walk us through really quickly what we're looking at here.
Yeah, sure. Thanks, Kelly. I'm happy to do so. So I think this is a similar situation to what we had in Stephen's quintet, where we are witnessing an interaction of a couple galaxies that have produced what you see here. So the understanding, so again, because Webb has given us an image at different wavelengths, we get this information about where the gas is in the galaxy and where the stars are. And so that's associated, you can see that here. So the blue-white light is telling us where the stars are, and the redder light is telling us where the gas is associated with it. And so my understanding is what's happened here, what we think has happened, is that you had a galaxy that was face on, where something else came right through it and caused a splash effect. Just like if you dropped a pebble in a pond and watched it in slow motion, you would see, you know, first a little explosion and then kind of a rippling effect go outward. And you're seeing that, where that's producing the ring in the cartwheel, and then the spokes are the leftover remnants of what probably were spiral arms, which have some cohesion and are still, you know, rippling outward as well. And so the fact that we see stars and gas traced in this means that it's caused some shocks to move through the gas, which also could be now birthplaces for new stars, exactly as the process that Christine was talking about, but you know, in a galaxy-wide kind of scale, not just in an individual nebula.
Cool. Anyone else want to talk about the cartwheel? It is really cool looking. And it took me until this was released to realize that it's supposed to look like the wheel of a cart and not someone like doing the gymnastics move. But there it is. It has a hub and spokes. Okay, so we have 2 minutes left, and we got a really great question for Kevin that we didn't have time to, but I'd like to circle back around to because I think it's a good place to end. So how can individuals be more involved with learning about exoplanets to support researchers and scientists?
Oh, that is a good question. Yeah, there's a couple of initiatives that have come up over the years where anyone, essentially anywhere around the world, can get involved in the discovery of exoplanets. So one of them is, for example, Planet Hunters tests. This is on zooniverse.org. And anyone who participates in this project would be able to search for, essentially become a planet hunter, transiting exoplanets. Right. And they can look at different light curves, looking for that dip in light, just like what we showed you earlier on in this session. And they could then discover their own exoplanet. Just a heads up, you probably won't get to name it yourself, but it is an exciting process, and I really encourage a lot of people to go there and check it out. It's a lot of fun.
Okay, well, thank you everyone for showing up for this panel. My apologies if you asked a question and we didn't get to them. There were a lot of great questions and we couldn't answer them all. Does anyone have any final thoughts they want to leave us with?
Go Webb!
Yes, go Webb. There's lots of more really great science to come. This is just our first taste of what Webb can do, and we have some really exciting, beautiful images, and there will be more in the coming months and years. So yes, thank you again to all of my panelists. You were lovely, and you did a really great job talking about the Webb images in science. And again, thank you to all of the audience members. I can't see you, but I hope that you had a good time and you learned something. So thanks, everyone. Bye.
Thank you.